Hi folks, for today's lesson you're going to need a blank sheet of paper and a writing utensil. So go ahead and get those out. Pause this video while you are retrieving those. We have two main goals for today. First one is we're going to learn how to draw endo and exothermic energy graphs showing chemical energy change and showing thermal energy change. And two, we're going to do a little bit of practice explaining why it is that chemical reactions are endothermic and exothermic based on the changes in chemical energy, whether the chemical energy goes up or goes down. Now, to start this off, on your paper, we're going to draw out an exothermic reaction. And so to start this off, what I want you to do is I first want you to draw a baseline at the bottom of your graph, and then I want you to draw a line showing the total energy in that graph. Now that total energy should not change. This is a closed system. Energy can't be created or destroyed. Label that as total energy, and then you'll have three parts to your graph. Above the graph, or you could do below, but we'll use above, I want you to label reactants, activated complex, and products. Go ahead and pause this video while you do that. Resume it once you've got that drawn out. First thing that you want to draw after you've set up your graph is you want to draw the chemical energy for the reactants. I like to draw it about halfway up. You could vary it a little bit, but you want to give enough space on both sides. Once you've drawn that chemical energy part of the graph, label it as chemical energy or CE, something to indicate its chemical energy. Then we're going to move to the activated complex. To go from the reactants to the activated complex, we have to break bonds. Bonds are attractive forces, so that means that when we break the bonds, we're pulling them apart, we're going against that attractive intramolecular force, and if you go against the force, the chemical energy must rise, potential energy. So you want to draw your graph for the chemical energy for the activated complex to be considerably higher than the original chemical energy for the reactants. It doesn't need to be above the total energy, it needs to have a little bit of space, but it needs to be very, very high. Next, you want to draw the chemical energy for the products. Two things have to be true. Number one, in all of our graphs, the chemical energy for the products has to be less than the chemical energy for the activated complex. Because when we're making products, we are making new bonds, we're moving with the force, the bonding force, so that means the chemical energy has to drop. Second, since this is an exothermic reaction, the chemical energy has to drop so the thermal energy will rise, increasing the heat, making it exothermic. That means when you draw out your graph for the chemical energy for the products, it has to be less than the chemical energy for the reactants. So whatever you have for the original amount of reactants, for the chemical energy in the products has to be lower than that. Finally, go ahead and fill in your thermal energies. Thermal energies are going to go from the amount of chemical energy you have up to the total, so that the chemical energy plus the thermal for each situation adds up to be the total. Label it as thermal energy. You could do THE or something like that just to indicate that it's going to be thermal energy. Go ahead and finish up your graph. Pause this video while you're doing so. Next, you're going to draw out an endothermic reaction graph. Similar to before, go ahead and set it up with your baseline, your total energy line, label your total energy, and label your reactants, activated complex, and products. Pause this video while you're doing that. Next, draw in the chemical energy for the reactants. Because this is an endothermic reaction, I usually like my original chemical energy for the reactants to be a little lower than half. It doesn't have to be, but you just want it to be sort of from the halfway point down toward the bottom. Go ahead and draw that. Pause if you need to. For the activated complex, it needs to be the same place that it would have been on your exothermic reaction graph. Near the top, chemical energy has to increase because we're breaking bonds going against the intramolecular force. Finally, for the chemical energies, draw the products, the chemical energy for the products. Once again, since we're making bonds, we're going with the force. The chemical energy for the products has to be less than the chemical energy of the activated complex. Since it's an endothermic reaction, that means the thermal energy has to go down to get cooler, which means the chemical energy has to go up for the products compared to the reactants. So wherever you put this chemical energy for the products, it has to be higher, a larger amount than the amount for the reactants, and has to be a smaller amount than the amount for the activated complex. I sort of put it in the middle. That's a good place to place it. Finally, what you want to do is fill up the rest of those graphs with the thermal energy, showing that we started with a lot of thermal energy, we ended with less thermal energy. Since the thermal energy dropped, it would have gotten cooler. Finish out drawing out your graph, and then resume the video once you've done that. For the next section, we've got a question for you. So for the following reaction, 2HF plus I2, those are our reactants, yields 2HI plus F2, are products. We know that the products have a lower chemical energy than the reactants. So we know the chemical energy has decreased as this reaction has occurred. I want you to draw on your paper a bar graph showing how the chemical and thermal energies change during the reaction. Basically, you're going to draw a graph up with all of the parts that we showed on the last two. So pause the video, draw those out, and then we're going to come back and we're going to take a look at a possible correct answer. All right, so one possible way of writing this is to, just as we did before, write out the reactants, activated complex, and products. We're going to put the 2HF plus the I2 above reactants, put the 2HI plus F2 above the products. We didn't talk about that before, but that's a good way to show what the reactants are and what the products are. Because of the fact we were told that the chemical energy of the products was lower than the reactants, that means the chemical energy on this side has to be less than the chemical energy on this side. We've done that. We also know that the activated complex has to be a higher energy. So take a look at this graph, see if this reflects what you have. If not, go ahead and make some changes to the graph that you have. One thing to watch out for, this is a common mistake that people make, is if we had a reaction like this, this would be an exothermic reaction because the thermal energy increases. Take a look at the graph that's on the left compared to the graph on the right. Both of these are exothermic because the thermal energy increased and the chemical energy decreased. That happened for both of them. The reason why the graph on the right is not a possible graph is it shows that the chemical energy of the activated complex was less than the chemical energy of the reactants. Because making the activated complex always involves breaking bonds from the reactants, moving against the force, the chemical energy of the activated complex always has to be greater than the chemical energies of either the reactants or the products. If it's in the middle, if it's below one of the two, then you know it's not right. So just double check to make sure that, like the graph on the left, the chemical energy of the activated complex is always the highest energy, chemical energy, that your graph shows. Next question. Draw a bar graph for a reaction that is more exothermic, that is gains more thermal energy than the last reaction, the one that you drew on the previous question. Go ahead, use your graph on the previous question as sort of a baseline, and on your paper, draw a graph for one that is more exothermic than that reaction. Pause the video, we'll come back and we'll take a look at a correct example. The graph on the left is what we basically drew the first time we did this. It's clearly going to be exothermic because the chemical energy drops and the thermal energy rises. But if we wanted to have one that's more exothermic, that means the chemical energy needs to drop by more and the thermal energy needs to rise by more. I made this chemical energy on this side drop by more by increasing the original chemical energy of the reactants and decreasing the final chemical energy of the products. So that means that the difference between where it starts and where it ends chemical energy wise is bigger on this one, making it more exothermic, and smaller on this one, making it less exothermic. So this graph on the right is one similar to the one that you ought to have if the graph on the left was your original. Let's look at this instead of from a graphical standpoint, from sort of an explanation standpoint. Same reaction. In this case, the products are going to have a lower chemical energy than the reactants. What I want you to do is on your paper, or you could type up, or for that matter, go ahead and you can put it into the question that's going to come after this. I want you to write a full explanation for why this reaction is endothermic or exothermic. I want you to start off with a good place to start. Because the chemical energy decreases in the reaction, ... Complete typing this out, and then we'll take a look at the correct answer. One possible answer you could have would be this. Because the chemical energy decreases in the reaction and the total energy must stay the same, the thermal energy must increase. Since the thermal energy increases, the reaction must be exothermic. That's really all it takes, just 2, maybe 3 sentences to be able to explain this. Notice that we start off always talking about what the chemical energy does, how it changes, increases or decreases. Using that and the fact that energy is conserved, we can then figure out what's going to happen to the thermal energy. Thermal energy increases, it gets warmer, it's exothermic. Thermal energy decreases, it gets cooler, it's endothermic. Now what I want you to do is on your paper, draw two sets of bar graphs. One for a very endothermic reaction, one for a slightly endothermic reaction. We say very endothermic, we mean one that gets a lot colder. Slightly endothermic, meaning one that gets just slightly colder. So go ahead and pause the video, draw those out on your paper, and then we'll look at some correct examples. Looking at the slightly endothermic, we've got on the left side, the chemical energy does rise going from the reactants to the products, but just by a little bit. And if the chemical energy rises by a little bit, the thermal energy has to drop by a little bit, making it just slightly endothermic. Note again, the activated complex chemical energy is higher than both the products or the reactants. For a very endothermic reaction, the chemical energy has to increase by a lot. Therefore, the thermal energy has to decrease by a lot, making it very endothermic. It loses a lot of thermal energy and we get much colder. Once again, note that the chemical energy, the activated complex, is higher than the chemical energy of either the products or the reactants. That always has to be true.